form at the same time, and so are observable physical evidence that this abundant nuclear decay had to have occurred at an accelerated rate. Now, this is all written up in detail in the second volume of the rate research, and there's other diagrams and there's a step-by-step explanation of the way in which the experimental data, there is experimental evidence that hot fluids, hot waters, go through the biotite flakes and are capable of transporting that polonium, where it nucleates in certain sites between the pages of the book nearby to produce those polonium radiohalos. So let me just run through it quickly again, because I want to take this a step further. In further research, I've actually been testing this idea of the formation of polonium radiohalos. I say, okay, this is a model for their formation. Now let me make predictions, which is what a good scientist does. He builds an idea, and based on that idea, he predicts what effects it will have in other situations, in other rocks, and then he goes out and collects samples to see if his predictions are correct. And this is exactly what I've been doing in research subsequent to the conclusion of the RATE project. So let's just run through this idea again of how the halos form side by side. We've seen that diagram before. The radiohalo, now an interesting extra thing in this is discovered that the radiohalos can only form below 150 degrees Celsius. Otherwise, the alpha tracks, the little particle damage trails, are annealed. That is, they're wiped out. Let me explain that to you. When the alpha particle goes through the crystal lattice like the wall, it damages the crystal. That is, it pushes the atoms of the crystal structure out of alignment. Okay? You heat the rock up, you heat the crystal up, what does it do? The heat transfers to vibrational energy of the atomic structure. So if you get enough heat, the atoms will vibrate sufficiently so that the atoms that have been pushed out of place will pop back into place, back to the original structure of the mineral, which will heal the damage caused by the alpha particles. So in other words, the dark discoloration disappears. Now, how do we know that's 150 degrees? Well, interestingly, in the same drill hole in New Mexico, where Russ Humphreys got those zircon crystals for his helium diffusion studies, as you go down that rock, that granite, they actually measured the in situ temperatures, the current temperatures in the rock as you go down. And they also looked in that granite at the radiohalos in that granite. And when they got to the depth at which the rock temperature was 150 degrees, the halos were faded. Below that, at a higher temperature, the halos had been eradicated from the rock. So in other words, temperature will wipe out these halos. The inverse to that is that the halos will not form above that temperature, because the atoms will be vibrating so much that the alpha particles will push them apart temporarily and they'll snap back into position again because of the energy from the heat. So that was an important clue, that they can only form below 150 degrees. Now, we've already said that the uranium radiohalo forms around the tiny zircon crystals. The uranium decay in the zircon crystals supplies both radon and polonium. Radon is the precursor in the decay chain to polonium. Radon is a gas. It's inert gas. It doesn't chemically bond with anything. And it has a very short half-life, but it's very soluble in water. So it also can be dissolved in the hot water coming along, just as the polonium will be in these hot water or hydrothermal fluids. So we have the hot water flowing along between the sheets of the biotite, between the pages of the book. It passes the uranium-rich zircon crystal that's producing radon and polonium, and they're dissolved. Okay. The hydrothermal fluids transport the radon and the polonium to adjacent deposition sites without leaving traces, and the polonium concentrates in new pockets called radiocenters, these new areas that form the centers of these halos. And as each polonium atom concentrates, it decays, but more polonium is coming in the fluids. So as each polonium decays from that site, another polonium atom comes. So rather than all the polonium arriving all at once, which Robert Gentry said it had to do, the hot water flowing through progressively supplies the needed polonium to form the radiocenter, the centre of that polonium radiohalo. So what happens is you have a sulphur atom or a chlorine atom sitting here between the pages of the book, and polonium just loves sulphur and chlorine, and so as soon as it gets there, it stops. Once it stops there, it decays, and then the sulphur doesn't have any polonium sitting next to it, but the water brings another polonium atom along. It holds on to it, but then the polonium decays, so now the sulphur is free to grab another polonium atom. And so over a short period of time, more and more polonium keeps coming across, decaying and producing that radiohalo. So that's this idea of hydrothermal fluid transport to form these polonium radiohalos.
So does polonium come out of the zircon?
Yes.
Helium would be diffused?
Yes. Yes. Correct. And so does radon gas.
Why does it decay so really quickly in the zircon?
Sorry?
Why wouldn't the polonium, like polonium...
Well, some would. Some does. And that produces the polonium rings around the uranium radiohalos. Okay? Some does decay doesn't get transported, and it forms the rings around the uranium radiohalos. Some doesn't, and it gets transported.
Can you measure the distance between the uranium halo and the polonium-210 halo?
You can measure distances. It's very hard. It's very hard to do it consistently by the methodology that I'm using, because what happens is you have to crush the rock and peel the flakes apart, and you don't always get enough of more than one halo in the fragment of the biotite crystal. It's only if you get some of those photographs were actually taken in whole rock microscope slides. So I haven't had enough samples or enough of those to do consistent measurements of the distances. But most of the distances are less than a few millimetres, or very much less than a millimetre, the distances between those polonium and uranium radiohalos.
You can calculate the velocity of the water?
Oh yeah, sure. Yeah, that's a potential possibility. So these are the implications. Fully formed uranium radiohalos require at least 100 million years worth of radioactive decay at today's rates. Only that much uranium would supply the polonium concentrations needed to form the polonium radiohalos. But as I said before, these isotopes, these atoms decay very rapidly. We've been through those. Radon only decays, has a decay rate of 3.8 days, so it's even shorter lived than polonium-210. So the polonium radiohalos had to form within hours and days. So as I said before, 100 million years worth of uranium decay had to have concurrently occurred as the uranium radiohalos formed. So the uranium decay had to have been grossly accelerated. But here's the next step. The granite has the uranium and the zircon in it earlier on as it's molten at temperatures of 650 up to 730 degrees. It has to survive while the granite cools to below 150 degrees before the water transporting the polonium and the radon can produce the polonium radiohalos. Okay, remember the radon and the polonium has only a short half-life. If the granite cooled slowly over millions of years, all the radon and polonium would have decayed away, and there wouldn't be any left by the time, or hardly any left by the time the granite got to below 150 degrees to be left to form the polonium radiohalos. So the implication is the granites had to cool within days as well. And I've developed this further. I'm going to present a paper on this at the conference in Pittsburgh. In fact, this is a diagram from that paper to conceptually visualise what happens. You have the intrusion of the granite at around 700 plus degrees. By the time the rock has cooled, the magma has cooled to below 600 degrees, all the minerals have crystallised, including the zircons with the uranium in them. The first release of the hydrothermal fluids, the hot water, is below 400 degrees, but the radiohalos that form from the transport by the hot water of radon and polonium will only form after the rock gets down to 150 degrees. So if the halos form within days, the granite also had to cool that rapidly, drop that temperature right down, otherwise you wouldn't have sufficient radon and polonium left to form the halos. It will all have been washed out of the rock and decayed away. Okay, I wanted to test this idea. Let me just go back to this for a minute. Okay, so if hot water in a granite produces these polonium radiohalos, what would it mean if some rocks, some granites have more polonium radiohalos in it than other granites? What would that mean? What would produce more polonium radiohalos? More zircons and more hot water. So you could argue that the more hot water, the more potential for more polonium radiohalos. Okay, so I thought I'd test this idea. In the Great Smoky Mountains, near the Tennessee-North Carolina border, we have sandstones, sand that's been turned to stone, sandstones. Not all of geology is complicated. And these sandstones have been metamorphosed. Now sandstone has no biotite in it. You will not find any biotite in sandstone. But in sandstone you find zircon crystals. Okay? On the east coast of Australia we have beach sands that are mined for zircon. You get sand with zircon in it. It's radioactive sand. Okay? Now, that means in the zircons you've got a source of uranium, but you also got a source of polonium. When these sandstones were metamorphosed, one of the products that was formed, the sand grains were bonded together with clay. There was a clay cement. When the clay was metamorphosed, the clay was transformed like a caterpillar is transformed in a butterfly. That clay was transformed into biotite. Okay, so we have zircon grains as a source of uranium and polonium, and now we've got biotite in these metamorphosed sandstones. And I thought, now what if there was water associated with a metamorphism? I might actually find polonium radiohalos in the biotites in this metamorphosed sandstone. We know they weren't created sandstones and that. These sandstones have fossils in them in other parts of the country. And so I went through that and I discovered also in the literature that not only was there biotite in this metamorphosed sandstone, but there were other minerals. In fact, as you went from northwest to southeast, from Gatlinburg to Cherokee, along the highway, you actually went through zones in the metamorphosed sandstones where there were different groups of minerals, metamorphic minerals. And at different places along the highway, there is a boundary where one group of minerals changes into a different group of minerals. And at one particular boundary, labelled with the word staurolite, which is a metamorphic mineral, at that line, that mineral is found in the rock as you go further to the right in that diagram. And why is it in that rock? Because there were slightly higher temperatures and pressures, and there was a mineral reaction. Well, this is what the sandstone looks like, the metamorphosed sandstone. There was my field assistant, Kurt Wise. And this is what the metamorphosed sandstone looked like, and you can see biotite flakes in there. Those greeny ones are biotite flakes. And there was a metamorphic reaction, a mineral reaction at that boundary. And what did we see? The mineral muscovite with the mineral chlorite reacted to produce biotite, staurolite, quartz and water. In fact, you can see from the numbers, there were 224 molecules of water formed to every 54 molecules of biotite. I thought, hello, I've now got water. I'm going to predict that I'm going to find more polonium radiohalos at that spot in those metamorphosed sandstones than anywhere else, because I've got a source of polonium in the zircon crystals, I've got a repository in the biotite, and now I've got hot water. Okay. Question?
You say that this process is producing water. Could that have been part of where the water for the flood came from?
Not in this instance, no. So we collected a series of samples going right across, and you can see that it's almost perpendicular to those zones of different minerals in the metamorphosed sandstone. So that's a traverse. Now along that line we plot the number of radiohalos. What I do when I do this research, I do a procedure where I can get a statistical sample where I approximately 1,000 biotite flakes for every sample that I examine, so that I can compare sample with sample to quantify how many halos. This is the result. Right where this boundary, where this occurs, there's 4 to 5 times more polonium radiohalos than anywhere else in these metamorphosed sandstones, where you had much more water. So that was a prediction. Because of the hydrothermal hot water transport of this polonium, I predicted there would be more halos where there was more polonium radiohalos, where there was more hot water flow. Sure enough, slam dunk. Prediction fulfilled. In fact, interestingly, there's some metamorphic rocks in Norway, in the Bergen area. These are former magma rocks, we call them igneous rocks, that are similar to granites, that had been metamorphosed at depth inside the earth to a high grade, that is high temperature, high pressure metamorphic rock called a granulite, early in the flood. And subsequently, during earth movements early in the flood in our time frame, hot waters had penetrated along fracture zones in this metamorphosed rock, transforming it into a different, along the fracture zones, the hot water had transformed the surrounding metamorphic rock into a different metamorphic rock. And this different metamorphic rock, called eclogite, is not known to normally have biotite in it, and certainly with no biotite it doesn't have any polonium radiohalos in it. But interestingly, let me just skip through these. Some of these rocks actually do contain biotite in this instance. In other words, as the fluids went through and the rock cooled, the fluids actually also produce some biotite in these shear zones. Okay. And the interesting thing was, I don't need to go into these technical details, except the geologists, and this was written up in the conventional scientific literature, in using the radioisotope dating methods on these rocks in this shear zone, they demonstrated that the hot fluids had been travelling through these shear zones over short periods. Initially they estimated 18,000 years or less for this metamorphic transformation in these shear zones, but they dropped it down to less than 10 years. And that was radical. This was written up in Nature But the interesting thing is the biotite flakes contained polonium radiohalos from the hot fluids transporting polonium in. And that have fitted the short time scale, probably even shorter time scale. There would have been the biotite formed due to these fluid flows, which must have also transported the polonium. But of course the polonium-210, they were polonium-210 halos, only have a half-life of 138 days, and therefore rather than 10 years for this metamorphic transformation, it would be in less than a year. So that fits the flood timescale for this metamorphic transformation. So now we're seeing that the polonium radiohalos are actually helping us not only show that granites can form rapidly, but also that metamorphism of rocks has occurred rapidly. So I've continued this research, and I just want to quickly show this to you and then we'll finish. This is what I'm going to present also at the conference in Pittsburgh in a couple of weeks' time. In southeastern Australia, we have a classic metamorphic complex. It's a classic textbook example in the geological literature of zones of increasing metamorphism, that is the metamorphosis of original siltstones and shales into what we call schists and gneisses, which are metamorphic rocks. And at the very centre of this complex, the temperatures were so high that the rocks melted to form a granite. And you can actually literally walk from outcrops of fossiliferous sediments that obviously were formed during the flood across these zones of increasing metamorphism of the original fossiliferous sediments until you get right into the granite in the centre. So this is a geologic map, and the town of Cooma is at the centre of the complex where the granite is in pink, and as you go out, the metamorphic rocks get lesser and lesser from the heat and the intensity. Walking the other way from the white area out to the left, you've got fossiliferous sediments. As you walk in towards the granite, you get higher and higher temperature transformations of the original siltstones and shales. Now, I'd already found radiohalos in the granite, so I was interested to see there was a reference in the literature to uranium radiohalos in some of the surrounding highest grade metamorphic rocks. But the interesting thing is there was evidence of zircon crystals all the way through those metamorphic zones, and there were biotite flakes in all those metamorphic rocks. So I thought to myself, okay, I've got zircon crystals that has uranium and polonium, I've got biotite flakes, I ought to be able to find polonium radiohalos. Particularly where there was more water, you would have more polonium radiohalos. Here's some of the outcrops of these rocks from road cuts. That's what some of the rocks look like under the microscope, and you can see some of the halos already in the biotite flakes. So there were polonium-210 radiohalos found throughout all the biotites, throughout all the metamorphic zones. But the polonium-214 and 218 and uranium radiohalos were only found in the highest grades of rock, the highest metamorphism, and in the granite itself. And the radiohalo numbers increased progressively inwards into the granite. In fact, I've got a diagram in a minute to illustrate that, and it matches the quantity of radiohalos matches the volume of hydrothermal fluids that would have been involved in both the metamorphism and the granite intrusion. So here's some of these radiohalos. That's in the granite. You can see the uranium, which are the bigger ones, polonium-210 in this instance. Remember, this road with the samples was a traverse through these zones. From the left is the lowest metamorphism, to the right is the highest into the granite. And this is what the plot of radiohalos looked like. It went up, it dropped, and then went up again. And I'm going to go into the technical details at the conference. But it's clearly, obviously related, it is related to the amount of water in the rocks when they were metamorphosed and when the granite formed and the rocks cooled to produce those radiohalos. So again, this is again illustrating that not only granite formation but metamorphism is a rapid process. Let me close with ongoing research. In Cornwall we have granites that contain huge numbers of polonium and uranium radiohalos. But the Cornwall granite also hosts veins that contain tin, copper, uranium, lead, zinc in fractures where hydrothermal fluids generated by the granite have carried the metals and deposited them in the cracks and the fractures. And so there seems to be the huge number of radiohalos reflects the large volumes of hot waters that were carrying those metals into those veins. It's interesting that in Robert Gentry's work there were minerals in Germany, fluorite mineral in Germany, which is another host of a mineral that hosts uranium and polonium radiohalos, and biotites in Canada that also had huge numbers of uranium radiohalos in them. What he didn't report was that these minerals are associated with hydrothermal uranium ore veins. The reason why he found so many large numbers of polonium radiohalos was because there was larger concentrations of uranium associated with these minerals. So the numbers of radiohalos in granites could also be used as a way of exploring for new ore deposits. And so my ongoing research at the moment is going to areas where we know there are mineral veins and looking at the numbers of radiohalos to compare the numbers of radiohalos with barren areas of granite where there are no ore veins. Because if I can demonstrate that the numbers of polonium radiohalos are related to the water volume that could transport the metals, it's a potential exploration method for finding new ore deposits. So don't let anyone tell you that creationist research doesn't have potential practical applications. So that's what I'm currently doing in my research, that these polonium radiohalos, therefore if they're associated, this is the other thing, if they're associated with the formation of these metal deposits and the polonium radiohalos form within days, it also means that the ore deposits formed within days. Okay, so this is why I titled the talk Radiohalos not only as evidence for accelerated nuclear decay, but evidence for catastrophic geological processes. One last diagram. This is in the final, the second of the rate books. I plotted here the conventional age of a granite with a number of radiohalos per slide, rock slide that I examined. And if you, just for a ballpark, decide that the pre-Cambrian granites, older than 600 million years, are pre-flood, and the granites above that are flood, and you might get a few at the end of the flood. Notice the numbers of radiohalos actually peaked during the flood. Now, why would you think that would be the case? Lots of hot water during Noah's flood. Well, let's conclude. Radiohalos provide evidence of hundreds of millions of years worth of decay at today's rate that has been accelerated. So they provide a new model for the rapid cooling of granites in 6 to 10 days, a new model for the rapid formation and cooling of metamorphic rocks in only days to weeks, a potential model for the rapid formation of hydrothermal, that's hot water mineral deposits, in only days or week. And of course these timescales for these processes would thus be consistent within a biblical year-long flood event only 4,300 or so years ago. You see where I'm going with this research? It's not only about showing that the decay rates were accelerated and therefore you can't trust the dating methods, but there are geological processes that our opponents have said to us, ha-ha, they took millions of years, now we're showing no. They only took days to weeks, and that is compatible with the biblical account of Earth's history. So not only are the radioactive dating methods unreliable and require a new model to account for much decay at accelerated rates within the scriptural time frame of Earth history of only about 6,000 years.